In my last video, we covered basic ADTs for VCE algorithmics such as lists, stacks, and queues. Here we cover graphical ADTs and when to use them. I'll also introduce some terminology and ideas that are not explicitly part of the algorithmic study design, but help you to read around the subject. It's important that we don't underestimate the importance of background knowledge, since you never know exactly what they'll ask in an exam. I'll warn you now, this video is quite dry and contains a lot of things to remember. I'd suggest using flashcards or at least watch this video a bunch of times to help things sink in. We use graphs to represent certain problems, among other things. A graph is a collection of nodes, also known as vertices and edges. In Algo, we only use simple graphs, where multiple edges and loops are not allowed. That is, you can't have two edges that link the same two vertices, nor an edge where both ends connect to the same vertex. Graphs can be undirected or directed. This refers to the edges. If an edge is directed, we can only traverse in one direction. This can also signify a one-way relationship between two nodes, such as in a project management graph, where one task can only commence after a particular predecessor has been completed. We have quite a few definitions to learn regarding graphs. A walk is a series of vertices that one can traverse in order, which means the vertices are adjacent. It can include repeated vertices and can start or finish anywhere. Imagine you're just out for a stroll in the evening sun with no particular purpose or destination in mind. A path is a series of vertices with no repeated vertices. Think of a path as wanting to get somewhere in particular. Imagine I want to catch a plane from Glasgow to Hanoi. Whilst I might have to change in London or Singapore, I wouldn't change in the same airport twice. A cycle is a path of at least three vertices which starts and finishes at the same vertex. It's important to distinguish paths and cycles from trails and circuits. Paths and cycles are about repeated vertices, while trails and circuits are about repeated edges. A trail goes from one vertex to another without repeating the same edge. And a circuit is a trail which starts and finishes at the same point. In these cases, you are allowed to repeat a vertex. Imagine a nature trail. You care about seeing all of the edges, not whether or not you visit all of the intersections. Tree is a graph that does not contain any cycles. In other words, is acyclic. We'll talk in another video about minimum spanning trees, which aim to connect all vertices using minimal edges. A tree larger than one node will have at least two leaf nodes, i.e. nodes with a degree of 1, where the degree of the vertex means the number of edges connected to it. A special kind of tree is a decision tree. We'll cover these in another video. There are two main ways you'll use graphs to model algorithmic problems. The first is where the nodes and edges represent actual real-life features, such as nodes representing airports and edges representing the distance between them. The second is a state graph, where we use nodes to represent iterations or partial solutions to a problem and connect them to other nodes, which can be reached in a single move. A game of tic-tac-toe is an obvious example of this. The original node is a blank 3x3 grid, and connected to it is every possibility that could happen on the next move. Connected to each of those nodes is every possible state of the next move, and so on. In these examples, you can see how we might want to assign a weight, representing a distance or a time. We can also assign nodes and edges any property we like, such as colors, strings, or arrays. Time for more definitions. A disconnected graph is one where there isn't a path between every pair of nodes, i.e. it's not possible to get from every node to every other node. A connected graph is the opposite of this. Be careful when defining this in exams. It doesn't mean that in a connected graph an edge exists between every pair of vertices, just that it's possible to get from every node to every other node. A bridge is an edge which, if removed, would disconnect a component of the graph. A complete graph is one where every vertex is connected to every other vertex by an edge. The number of edges is given by n times n minus 1 divided by 2. To explain this, imagine a graph with 5 vertices. Each of those vertices can be connected to 4 others, giving us 20 edges. However, doing this will double up the number of edges, so we need to divide the result by 2, giving us 10 edges. Recall that paths and cycles have no repeated vertices. Hamiltonian paths and cycles, the additional constraint of visiting every vertex in the graph. This takes us to a classical computer science problem, the travelling salesman problem, where we aim to visit every vertex with no repeats in the shortest possible time. We'll see later that this is a very hard problem to solve. Sometimes we just want to know whether or not it's possible to do without any repeated vertices, and other times we want to find the minimum possible cost. Similarly, Eulerian trails and circuits allow us to visit every edge without repeating any edges. Trails can start and finish at any vertex, whereas circuits must start and finish at the same vertex. This leads us to the Chinese postman problem, where we aim to traverse every edge and return to the start in as little time as possible, while possibly repeating some edges, because the postman needs to walk up and down every road to deliver letters. Two graphs which are isomorphic are the same, in that each vertex from one can be mapped to a vertex in another, such that all of the same vertices are connected to each other. The thing to learn from this property is that graphs are not stored in the way you draw them. For example, if you use a graph to represent a 3x3 grid, you need to add a node property to make it clear which part of the grid each node refers to. One graph is a subgraph of another graph if it contains only vertices and edges that exist in its parent. It's very similar to the use of the word subset in mathematics. A bipartite graph is one where the vertices can be arranged in two sets such that no edges exist between vertices in the same set. This doesn't come up much in VCE Algorithmics, but is helpful when practicing graph theory proofs. Finally, we define the diameter of the graph as the longest, shortest path between two vertices in a graph. That is, for each pair of vertices, find the shortest path between them and add it to a list. Then choose the longest one from that list. Again, never seen in an algo exam, but you never know. Like our previous ADTs, graph ADTs have associated signatures. All of the same principles apply. We specify the inputs and outputs using basic types and not the actual names of things. Pause the video and have a read to see if you can work out what they do. That's given you a summary of ADTs for VCE Algorithmics. Later on, I'll go into more detail on things like decision trees, adjacency matrices, and conditions for Eulerian trails and Hamiltonian cycles. Leave a comment if there's something you'd like to see explained in more detail.